I'm standing in the sample area of the LoKI instrument. LoKI was designed specifically with the soft matter, materials and bioscience, the scientific communities in mind. It is a small angle neutron scattering instrument. We detect scattering from samples at very small angles. Those very small angles correlate to the structure inside the sample from a nanometer to a couple of hundred nanometers. And what happens is we have a very narrow beam that's collimated and fired towards the sample. It hits the sample, most of it goes through, and then a small amount of it scatters. That's collected on these giant two-dimensional detectors. In LoKI we'll have 9 of them, and within that two-dimensional pattern we have structure. And then when we talk about the type of samples and systems that we're expecting to investigate, biological samples, so we're talking your proteins, your viruses, your lipid vesicles, your soft matter, so your colloids, surfactants, your polymer self-assemblies, and then for your materials, so again things like gels through stretching. So this is kind of the community we're going for. Of course, if it fits in the beamline, everything is really possible. And more we're starting to see people bring in real life examples. For example, your foods. I personally measure things like pasta on a beamline using these beamlines to understand what's going on at the nanometer or the micrometer scale. Or we have industrial users who might come in and, for example, the virus capsid vaccines have been measured a lot in these type of beamlines in order to understand their structure and how that relates to their function whenever they're injected. These things are all the structure-property relationships between how something is structured at this minute scale versus how it behaves at the larger scale is extremely important. Part of the reason that LoKI is so special is because we're all about the flux. We want more neutrons, we want to get as wide a simultaneous Q range as possible, taking advantage of the ESS source. And that allows us to, in a single shot, take images quite fast of our samples to understand our systems at a much shorter time scale than can be done elsewhere. That'll mean that we have our samples placed here. We can have them under different conditions. So they might be under flow, they could be undergoing dramatic temperature changes, to pressure changes, all of these things that might happen on reasonably fast timescales. You could easily measure at an X-ray source if your sample environment allowed, but a lot more difficult to measure at neutron sources because you either have to repeat the experiment many times, or you can't really get to that fast timescales. So our user community is particularly excited for that ability to do that. Also, because it's a higher flux, we should be able to measure more samples faster. So we expect the beam times to be shorter. We need to work through understanding automation of samples to get it to process a lot more, which hopefully means that we can get users their data faster, ideally high quality of data. So for weekly scattering samples, we should be able to get more statistics on them. Our ISSR is essentially done now, so that means that we've passed, the instrument is constructed, the safety features are all installed and tested, and if we were to get neutrons tomorrow, we'd essentially be good to go. That's an excellent milestone for us, but that technically doesn't mean that the instrument and the setting up of the instrument is over. So for this next period, until ESS starts online, what we'll be doing is we're fine-tuning, we're developing things like the instrument control software, which works, but there's a lot of things that we can add to it to make it easier performing and easier for users. But actually a large portion of our work will really just be preparing for hot commissioning. A lot will become clear whenever we finally get neutrons, and we can see things like, have we shielded in the right place, how well do our detectors work, can we sort out the alignment any better, and things like that. So a lot of our time now is going to be spent on planning that and essentially robustly testing everything that we've already tested so far. So once we get neutrons, once we commission the instrument and we're confident that it works, straight away we'll start testing samples, because it's the best way to test how well an instrument works is both by measuring new samples and also comparing it to how other instruments perform. So we're already in the process of planning those early experiments as well.